So last week we started the extremal set theory, and the extremal aspect of set systems we cared about. Given the system of sets, what we cared about is how the members, the sets in this system, they intersect each other, their intersection pattern. And we introduced last time very useful inequality proved by Bolobash about set pairs. Let's recall that. The Bolobash set pairs inequality. It says that we have pairs of sets A1, B1, AM, BM. Okay, satisfying that AI intercept BI is empty. So the same index ones are not disjoint, but different indices, they are intersecting for any I not equal to J. And if this is the case, we have this inequality that when you sum over everything, I in M, 1 over this binomial coefficient is at most 1. And this is similar in some sense to LYM inequality we've seen in the introduction part. You can use it to derive that. We also saw some applications of this. Apart from implying LYM inequality, we can use it to bound to find the exact answer for saturation numbers. We will see more applications later. For now, let's move on to some other contents. So let's first see, so recall that we can use this to prove LYM. LYM can be used to prove a Sperner. Yeah. So let's see an application of a very nice application of Sperner's lemma, which at first glance has nothing to do with Sperner's theorem. Okay. So before I conclude for now the Bolobash set pair inequality, let me mention the open problem. So here an open problem. So let's do a definition. We say a system of pairs of sets like this. AI, BI, a pair of sets is intersecting set pairs. Let's say AB uniform intersecting set pairs if each AI is of size A and each BI is of size B, and it satisfies this set pair inequality in Bolobash theorem. Very good. And we know for such ISP, the number of pairs is at most A plus B choose A. So now this open problem is about, what about the size of the ground sets? How many elements can appear in such AB uniform ISP? The question is, what is the maximum ground set of an AB uniform ISP? So this is a quite conjecture of Tuza. Let me remark. in the 80s. Tusa obtained the bound on the maximum size of the ground set of AB uniform ISP within a constant factor of 4. So narrowing down this gap, lower and upper bound, closing this constant factor of 4, I think it's interesting. So for those interested in this problem, you can look up the literature. And likely, I will list this as one of the open problems for our student summer research program. Okay, so let's move on to applications. Let's first see an application of Sperner's theorem, a very nice one. Okay. Application of Sperner. Recall, Sperner's theorem says if you have A, which is an anti-chain in 2 to the n, meaning that no set in A contains another set in A, then the size of A is at most n choose n over 2, with maximum being the middle layer. Okay. This application is the Littlewood-Offord problem. The Littlewood-Offord problem bounds the atom probability of Rademacher sum. It's an important result in random matrix theory, and it is used, for example, to bound the singularity probability of random matrices. Useful in random matrix theory. In particular, bounding singularity probability of random matrices. Okay. So let's first recall what is a Rademacher random variable. It's very simple binomial random variable taking values between 1 and -1. Rademacher random variable, it takes value 1 or -1 with probability 1/2. Very simple one. Now, the theorem says, this is the theorem proved by Erdős, proved it using in the 40s, that given non-zero integers, could be positive, could be negative. And given a set of IID, identically distributed Rademacher random variable, this plus minus ones, and x1, xn, b, IID, Rademacher random variables. Then we can bound the atom probability from above, meaning if you look at the probability of this random sum from above, okay? So here, let's pause for a moment. What is this guy? So here, xi is Rademacher random variable. So you think of it as we wanted to look at the sum of ai, but with random sign +1 or -1. And we want to see the atom probability means the probability that this sum takes a particular value. So taking the supremum, we want to say we want to bound the probability that it has a particular value, okay? This is the atom probability. We want to say that this is not too large. By Stirling's formula, so let's recall, Stirling's formula implies that if you look at n factorial, when n goes to infinity, this is asymptotically 1 plus little 1 times square root of 2 pi n times n over the natural number e to the power e. So what this is saying is that it's of order of magnitude, if you do the calculation, 1 over square root n. So when n tends to infinity, this goes to 0. In other words, when you sum up more and more numbers with their signs randomly permuted, taking +1 or -1, the probability that the sum takes a particular value tends to 0. Okay. How do we prove this? Any question about the statement? Let me open the chat. Okay, so one last question. Okay, so, right. At the first glance, you see, this is something about probability. It has nothing to do with this anti-chain or anything. So how are we gonna go about proving this? This is the smart idea of Erdős. Basically, in the future, if you see something like +-1 and you have n choices, or 0, 1, right? We can have a natural correspondence to this Boolean cube. How? You can think of, because there are n coordinates, here, you have n coordinates, then you can, each one of these signings of +-1 of n coordinates, n sets, correspond naturally to a subset of n by just looking at those that assign 1. Then we can somehow link these random signs to a subset of, so the idea is to link a random sum, a random sum to a subset in n. Okay, here's the proof by Erdős. So there are 2 to the, as I said, there are 2 to the n choices for the random Rademacher variable signs x1 to xn. Okay. So let's fix z. natural number and see what are those choice of signs that will result in this particular value z. And let S, usually we write 0, 1 to the n for the hypercube, but in this case, we just write -1 to n, no problem. -1 to the n, the hypercube, be the set of choices be the set of all choices which give you the random Rademacher sum AIXI I in n equals to z. Okay, then what is this probability? Since each xi is randomly, each choice of sign, combination of n outcomes of this guy, is uniformly distributed over here. So each sign takes probability 1/2 to the n. So this probability is exactly the total size of S, total choice of these signs, divided by the total choice of all signs, 2 to the n. This implies that the probability, the sum of AIXI equal to z equals to size of S over 2 to the n. It suffices to show size of S is at most n choose n over 2 flow. And now I already told you it's about applications of Sperner's theorem. In other words, it suffices to show S as a subset of the hypercube is an anti-chain. If it's an anti-chain, as I said, again, we should think of this as 0. So S corresponds naturally to a subset of S, of N. If it's an anti-chain by Sperner, it has size at most is, right? By Sperner, suffices to show so now this is our goal. So far, so good. And this is simple. By symmetry of Rademacher sum of Rademacher random variable, it takes same probability to be 1 or -1. So when you look at this, by flipping the signs of, by flipping this xi symmetry, we can assume all AI are positive. We may assume that all AI, A1 to AN, are positive. If it's negative, you can build a one-to-one injective bijection to another choice of AI and the signs to make sure that those are positive. I'll leave it as exercise if this is not clear. So we may assume they are all positive. Okay. Now, as I said, identify S with a subset of N, i.e., if xi is 1, I in S. Xi is -1, I is not in S. All right, this is the correspondence, as I said. Now, let's see why S is an anti-chain. Our claim is that S is an anti-chain. Then we finish the proof. Suppose otherwise. Suppose is this two elements. Two sets, y, which is a subset of another y prime. Okay, so how does y looks like? Y looks like y1 to yn. This looks like y1 prime to yn prime. What does it mean? It's a subset of that. That means whenever you see a 1 here, it's also a 1 here. If you, okay, and if you have -1 here, this could be 1, could be -1, we don't care. This means it's a subset of that. Then we imply what? First of all, they are both in S. And the choice of S means the sum of AI, yi equals to Z equals to the sum of AI, yi prime. That's the choice of S. So their difference is the same, is 0. They are both summing up to Z. Okay, since this is because y prime is in S. But what is this? As I said, whenever you have 1 here, you get 1 here. So forget about these ones, the same ones. You just look at the -1 where you have positive ones here. You get this difference is 2 times those where they differ, right? So this equals to 2 times the sum of I that's in y prime, but not in y, AI. But we assumed by symmetry that AI are positive. And we assume this is a proper subset. So this is non-empty. Implies that this is positive, a contradiction, finishing the proof. Okay. A very nice application of Sperner's theorem. So in the future, whenever you see a plus -1 to the n or 0, 1 to the n, naturally corresponds to this Boolean lattices, hypercube. Any question about the proof? And from the beginning of the course, we've been always saying that whenever we see a statement, we should always ask ourselves, is this bound optimal? So we should ask ourselves the same question here. Is earliest results the best possible? Can we have a lower probability for this atom, lower atom probability for random Radman-Hassan? And the remark here I want to make is that this is indeed optimal. Remark. This is optimal. Bound here is optimal. Okay, so what does it mean this is optimal? That means, let's look again. It's optimal means we need to find the choice of AI and find the choice of Z, showing that the atom probability, the probability that this random sum equal to this particular Z is at least this order of magnitude. So you cannot make it smaller. And that's very simple. If you think a little bit, consider all AI equal to A. Let's for a minute assume n is even. All AI to be the same number A, and let's let Z to be 0. So the probability that the sum of I in n, AI xi, let's rewrite it, because we take all AI to be the same A, is just the sum of xi times A equals to 0. This equals to right? And A is fixed, so you can cancel A from both sides. This is just the sum when the random +1 -1 equal to 0. This is exactly when half of them are +1, half of them are -1. Happens when n half are +1, n half are -1, which has probability exactly n, or n choose n over 2, and you have 2 to the n choices for ±1s. Good. So Sperner's theorem is about anti-chains in this hypercube ordered by inclusion, subset inclusions. Sperner's theorem. We can consider a more general discrete structure than this hypercube ordered by subsets. Notice that this hypercube, right, you have n on top, empty set at the bottom. You think of order them. If one is a subset of another, you can compare them. But sometimes you have two, they are not comparable. None is a subset of another, as in the anti-chain. This is actually a very special case of a structure called posets. Let's now formally introduce them. Posets. Posets is short for partial order sets. Okay, partial order sets. So if you take the initial poset, partial order set. So what is this? Partial order set is a pair. P and a binary relation. So formally, I should write like this, but when it's clear, let me just write P and less sign. This is a when the underground set P is clear. Let me suppress this subscript P. So poset is a set. Formally, is a set P. It's a set of elements P together with a binary relation, this less sign here, that is satisfy 3 conditions. Reflexive, meaning for every x is less than itself, you should think of them as comparable. X is comparable to less than itself. And anti-symmetric, meaning that if x is less than y and y is less than x, then they have to be the same elements. The most important one is transitivity, transitive. Transitive means what? If you have x less than y and y less than z, you must also have x is less than z. Okay? These 3 properties. So I will give you some examples shortly, but let's just briefly mention. This is kind of like why it's called partial order. If you think of natural numbers 1, 2, 3, 4, 5, 6, and the natural ordering 5 less the standard less, strictly less sign binary relation. This is a total ordering. every two natural number is comparable. But it's called partial order, means not every pair is comparable. For some pair, we have A less than B, if you think of as Boolean letters, where you have subset containment. But for some pair in the middle layer, no two contains another, so they are not comparable. So partial order means only some pairs are comparable, some pairs are not comparable. And this comparison should admit this transitivity, which is also natural, because in our natural number ordering, 1 less than 2 less than 3, if 2 less than 3, 3 less than 4, of course 2 is less than 4. This is mimicking what we have in the natural number, the transitivity. Okay, so the partial comes from, so we should compare this to this natural number with the less. This is totally ordered. Okay, 1, 2. And the transitivity becomes natural. I will not write these comments. Keep this in mind. Let me give some more definitions. Okay. Maybe let's see some examples right away. Examples. We have already one example. The first one is called Boolean posets, which the ground sets are 2 to the n, and the binary relation is subset containment. Okay. This is the Boolean poset. Let's quickly check. A set is a subset of itself, reflexive. If A is a subset of B and B is also a subset of A, then AB must be the same set, obvious. Transitivity, A is a subset of B, B is a subset of C, then A is a subset of C, obvious. This is an example. Second example, let's again look at natural number, but now not the standard less sign binary relation. We look at divisibility. If A divides B, we say A is less than B. Okay, so look at, this is sometimes called divisibility letters. Natural number n, and you have binary relation, which is division. In other words, if A divides B, then A is less. Well, here, when I write this, I mean this poset P is this guy, yeah? Let me write like this. So P equals to N and A less than P if only A divides B. And this is obvious also. If a number divides itself, if A divides B, B divides A, they have to be the same number. If A is a factor of B, B is a factor of C, then A is a factor of C. Also obvious. Let's draw a little bit. How do we draw posets? We usually draw posets from down to up. If an element is small, we draw it down here. If A is less than B, we write like this and link it by an edge. So when you go higher and higher, the element gets larger in terms of this binary relation. If they are not comparable, you don't put an edge between them. A and A prime, not comparable. You just don't do anything between them. So this diagram, if you draw here in terms of, we draw it in this Boolean lattice, right? If n equal to 3, we have seen this one. This is n equal to 3. You have empty set 3. This is 1, 2, 3, 2, 3. This is 1, 3. This is 1, 2. Okay. So this one and this one, they are not comparable. 1 is not a subset of 2, 3, not the other way around. There's nothing in between. And if this is a subset of that, this is a subset of that, you have transitivity. Empty set is a subset of 1, 2. Here, let's draw also a picture for divisibility. What's the smallest at the bottom? 1. Nothing divides 1 apart from itself in natural number. It's this is an infinite poset, right? So I can only draw so much. So 2, 3, 5, 7. What are the first layer? Are the prime numbers above 1. And then above 2, you have 4. Right? Above 4, you have 8. The only divisor of 4, 8 is 4 and 2 and 1. And above 2 and 6, 2 and 3, you have 6. 6 divides both 2 and divides 3. So you go like this, right? So on and so forth. You have 9 and 2 and 5, you have 10, dot, dot, dot. I will not draw further. The third one, example, in linear algebra, if you have a vector space V, then a vector space V, if you consider the set of all subspaces of V, these are the elements in your posets. Each subspace is an element in the poset. And how you order them? Similar in the Boolean poset. If a subspace is a subspace of another subspace, then you subspace containment, right? Ordered by subspace containment. Here are 3 examples. I encourage you to think of more examples. Good. Let's define some natural invariants for posets. What are the important invariants? So given the posets P and binary relation, we've already seen anti-chain. In the Boolean letters, anti-chain means no set is contained in another. So we say 2 elements A, B are comparable if A less than B or B less than A, right? If one of these satisfied, you can compare them. Otherwise, incomparable. Otherwise, incomparable. So anti-chain, in other words, we can generalize to abstract posets by saying a set of elements in P is anti-chain if nothing is compared to another. An anti-chain subset A in P is an anti-chain if elements of A are pairwise incomparable. And chain is the opposite. They are pairwise comparable. a subset C in P is a chain if elements of C are pairwise comparable. Then one thing to notice is that by transitivity, if elements are pairwise comparable, they are actually totally ordered, right? So in other words, maybe let me make a remark. So given a chain, for any chain, transitivity of the poset implies that C is totally ordered. We can order the elements in C. Let's say they are elements x1, x2, x r, let's say. Heute. Yeah, let's see. Suppose the element of this chain is x1 to xr. We can totally order them. We will call the size of the largest size of anti-chain, we'll call it width of the poset. How wide it is. The largest anti-chain is the width, and the largest chain is the height of the posets. Largest chain is the height of posets. This is the standard definition. Okay. Now we can talk about a very important result in about posets, a duality statement. So how do we talk about this duality statement? Maybe let me make a separate definition. Given the poset, this is a poset, chain or anti-chain decomposition of P is what? It's just you decompose the elements of P into disjoint chains or anti-chains respectively. So if it's chains, then let's say it's disjoint union of C1 to CT, say. If it's anti-chains, you partition into disjoint union of anti-chains, let's say S of them. All the elements are involved. Very simple thing. What's a trivial chain or anti-chain decomposition? You can just take a single element of the poset P. Every single element, by trivially, it's a chain, and it's also an anti-chain. So you can partition them. But this is not very interesting. A trivial, let's make a a simple observation about chain or anti-chain decomposition. Here's observation. For any chain decomposition, let's say partition into T chains, and then you take any anti-chain, A in P, then we must have the size of the chain decomposition is at least the size of any anti-chain. Okay, in other words, T is at least size of A. This is a simple observation. Why? So it's always good to keep this picture in mind. So if you have a poset, this is your chain decomposition, C1 dot 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 to CT. You partition your poset P into these chains. Each one of these chains is totally ordered, so you can they're pairwise comparable. Now you take an arbitrary anti-chain. Because here every pair of elements are incomparable, they have to go to every elements in A has to go to different chain. No two of them can belong to the same CI chain. So that means the number of these chains has to be at least the size of A. It's a very trivial inequality. Since elements of A has to have to lie in distinct chains in any chain decomposition. A simple observation. Very good. So the next theorem I'm saying is that since this is true for any chain and decomposition and any anti-chain, this is also true for the minimum size chain decomposition and maximum size anti-chain. So if you take a minimum chain decomposition, its size is at least the maximum size of anti-chain. The next theorem I'm saying is that, in fact, equality holds. We have the mean of this equals to the max of that. Some sort of duality statement. This is Dilworth's theorem. The famous Dilworth theorem is a duality statement stating that, inferring that the equality holds for minimum chain decomposition and maximum anti-chain. So here, let me state Dilworth theorem. Exactly what I just said. For any posets, the maximum anti-chain equals to the minimal chain decomposition. Let me draw an example. Let's again look at this size 3 Boolean poset. Okay. So what is the, by the way, we gave a name to this maximum size anti-chain. It's the width. The width of P, size of largest anti-chain, equals to the minimum size chain decomposition. So here the width obviously is 3. Size of the largest anti-chain is 3. For example, we can take this anti-chain to be one of this middle layer. This is my anti-chain. 1, 2, 3, singleton, incomparable. Let's look at chain decomposition. Let's decompose it into blue chains. So you can take, for example, this chain. What do I do now? And then this chain. And then this chain. Right? Then I cover everything. This is covered by the first one. This one covered by this one. And this, the last one. We have 3 chains in this one. So try to draw more examples yourself. We will see a proof of these and some applications, but first, let's see. Let's give a first round of simple applications. What's the simple applications? Well, simple application is that by Dewey's theorem, if sometimes people try to ask you, what is the width of this poset? Meaning you have to find out the size of the largest anti-chain. It's enough to find a chain decomposition that has the same size of the anti-chain. Because we always have this inequality. If you find 2 that have the same size, that means equality must hold. And the right-hand side must be the minimum one, and the left-hand side must be the maximum one. Okay? So by Dewey, if we can find a chain decomposition and an anti-chain of the same size, then automatically it implies that this chain must be we can find the width of the poset P. This chain must be the largest anti-chain. Here's an example. Let's do some examples together. The first example is the width of Boolean function, Boolean posets. This goes both ways, all right? Sometimes what I'm saying is people could ask you 2 types of questions. They could ask you, what is the largest anti-chain? And sometimes it's hard to find largest anti-chain. So we just need to find the chain decomposition, same size as anti-chain. You know that it's the largest size. Sometimes people could ask you, what is the minimum size chain decomposition? And it's hard to find out what's the minimum size. But all you need to do is to find 2 anti-chain equal to the chain decomposition. Then you know that this size of the anti-chain must be size of the minimum chain decomposition. So here, even though for n equal to 3, it's easy to find chain decomposition, when n gets larger and larger, it's very difficult. At least it's not obvious at the first glance. When you have a huge n, what will be a chain decomposition? You need to partition it into elements of chains. Not obvious at first glance. But we don't need to do that. To find out the minimum chain decomposition of a general Boolean poset for any n, it's enough to look at its largest anti-chain. And we know what's its largest anti-chain by Sperner's theorem, right? So width of the Boolean lattice equals to n choose n over 2 by Sperner theorem. This implies that the minimum chain decomposition of the Boolean lattice is of size n choose n over 2. Actually, something stronger is true. I will leave it as exercise. You can find a symmetric chain decomposition of size these. Each element of the middle layer lies in a chain. In this symmetric means that the starting point and ending point of every chain, its relative position in the poset, they have the same distance to the bottom, and the largest is same distance to the top. I will make it rigorous in the homework. Second example. What's the width of this poset consisting of the first 2n elements ordered by divisibility? The divisibility poset truncated at the first 2n elements. So we just need to find as I said, it's easy to find anti-chain, but it's not easy to determine what's the maximum size. It's easy to find chain decomposition, but it's not sure whether this one is the minimum size. But if we happen to find one, they are of the same size, you automatically know this is max, this is min. So in this case, to find out what's the largest anti-chain size, we just need to find anti-chain of these posets that has the same size as a chain decomposition. Anti-chain is easy to find. Here's the anti-chain of size n. You just look at the last half. If you take the last half of this interval, 2n, nothing divides another because, yeah, if you times 2, you go out. Very simple. So we just need to, if we can somehow find the chain decomposition of this 2n by divisibility chain of size n, then we know this will be the largest poset, anti-chain. So here is a chain decomposition of size n. How do we decompose it into chains? You just look at all the odd elements. All numbers, 1, 3, 5, 7, dot, dot, dot. So for x odd, each odd element in 2n, you look at the chain of its containing it, which is x times 2 to the I, where I equal to 0, 1, 2, dot, dot, dot. So this goes to 2, 4, 2 times 3, 2 squared times 3, 2 times 5, 2 squared times 5, 2 times 7, 2 squared times 7. This covers everything, because no matter which number you take here, you can divide it by some power of 2 to get down to an odd number. And how many odd numbers? N of them. So we get the chain decomposition of size n, and we know this must be the max, and this must be the mean. These two are the same, so we have this is max. We have this is mean. Good. This is simple application. Another application of Dilworth is, here's an exercise. You can use Dilworth theorem to prove before this, let me first make a remark and then I'll say this. Dilworth theorem can be also viewed as a Ramsey type statement. A corollary of Dilworth theorem is a Ramsey type statement. Illustrating a phenomenon that more structure implies better quantitative Ramsey statement. What do I mean by this? Let me write down this corollary. So for any posets, this is my posets. Now you take, let's say width is W of these posets. So you have, what does it mean? That means I have a chain decomposition of W chains. The largest anti-chain has size W, and I also have a chain decomposition decomposing P into W chains, C1 to CW. Each one of this chain is at most the size of the height, right? Height is the longest chain. So that means longest chain times the total number of chains is at least the total number of elements. So this implies so what we have is n, the size of P, equals to the sum of Ci, I goes from 1 to W, which is at most the height of the anti-chain times the width of the anti-chain. Okay, this implies the following corollary, that for any posets or n elements, then it always contain, there exists a chain or an anti-chain of size at least square root n, right? Either the width is at least square root n or the height is at least square root n. Why you can think of this as Ramsey? Ramsey says if you color complete edge of a complete graph by red or blue, what's the largest monochromatic clique? All the edges are same color. You can think of this also as a coloring of the edges, where an edge is colored red, say, if they are not comparable. You can color it by blue if they are comparable. Then the red clique is an anti-chain, and the blue clique is a chain. So okay. The important remark here is that in this red-blue coloring, when it corresponds to a poset, we can get square root n clique. So if we color edge set of Kn by comparability of a poset, meaning red incomparable and blue comparable, we get the clique is a chain, independent set is an anti-chain. So we have a square root n size monochromatic clique. This is much, much larger than standard Ramsey. Standard Ramsey, if you consider arbitrary edge coloring, not corresponding to poset, but arbitrary one, it's between two, actually now it's 2 minus epsilon times log n, and the largest monochromatic clique is between 2 times log n and 1/2 times log n. Here, this log n is base 2. Okay. So, we've seen this one in the introduction part by a random coloring, showing that you have a exponentially large random coloring without large monochromatic clique. And this is not so hard to prove. 2 minus epsilon is a recent breakthrough, but with 2, it's not hard to prove. I will encourage you to do it as an exercise. So for generic coloring, we cannot do better than logarithmic. But here, once the coloring is associated to this poset structure, you have polynomial square root n, much, much larger than this. This is what I mean here. This phenomenon is, which is intuitive. When you have more structure, the coloring associated to poset, you have better quantitative Ramsey. As an application of Dilworth, which is an application of this corollary, proof Erdős-Szekeres. Monotone sequences. It's very simple exercise. Okay. In the rest of this time, let's start by proving an easier version, which is the dual of Dilworth's theorem, Mirsky's theorem. So, well, what is the dual of Dilworth's theorem? So for some of you already probably were wondering why we take this anti-chain here and take chain decomposition. Why not anti-chain decomposition and compare it to a chain? Okay. Well, that's exactly what Mirsky's theorem is doing. The dual of Dilworth's theorem is Mirsky's theorem. So if you have a chain, take any chain and any anti-chain decomposition, okay, anti-chain decomposition means you partition your posets into pairwise incomparable anti-chains. Okay. We should have inequality going, a simple inequality going one way. If you have a chain, it should be this way, I think. Whenever you take a chain, all the elements in the chain are pairwise comparable. So that means for any chain decomposition, the elements of the chain has to go to different anti-chain, right? So that means the number of anti-chains needed to cover all elements needs to be at least the size of the chain. This is trivial. And Mirsky's theorem is saying, if you take the max on left side, it equals to the mean on the right-hand side. I want to study with Mirsky theorems because it has a simpler proof than Dilworth's theorem, even though they look very similar. So that's proof Mirsky's theorem first. The idea, let me first write the idea. It can be summarized Mirsky theorem into one sentence, the idea. So as long as you remember this one sentence, you remember the proof of Mirsky's theorem, is that for every element in the poset, you can define its height, which records the longest anti-chain ending at this element. So this height function, if you take the level set, that will give you a chain decomposition. Consider level sets of height function. Okay, let me illustrate this idea. Proof. Let's define this height function h that goes from the assigns each element in the poset P by some natural number in N. So for every x in P, it get mapped by h to hx, which is the height, which is the size of largest chain ending means with max elements being x. Here's the picture. You have your posets P, and your x is somewhere here. You look at the longest chain, which ends at x. And the number of elements in this chain is the height of x, some natural condition definition. Now, the idea is that if you look at the level sets, what's the level set? That's the inverse image of each level, I. They are anti-chains. All we need to do is to prove this claim. For every I, if you look at the inverse image of HI, if they are of the same level sets of H, it's an anti-chain. And how many level sets are there? The number of this image, largest image is the height of the posets, which is the size of the longest chain. So that means we can decompose P by level sets, which are anti-chains. We find the anti-chain decomposition of size largest chain. These will give you the conclusion as the number of level sets equals to the height of the poset P, which is the size of largest chain. The proof of this is also simple. Suppose, so we just need to prove the claim, we are done. Suppose otherwise. If not, let's say K equal to Hx equal to Hy, but X is less than Y. It looks something like this, right? You have Y here, and they are comparable. X is less than Y, but the longest chain ending at X and longest chain ending at Y, both is of size K. Here's a contradiction. Then I don't go, I go this chain, Y to X, and then longest chain. This is still a chain. It has size K plus 1, contradicting to the height of Y is K. That's it. Then consider the chain Y, X, and here, how do I write it? Consider the chain Y union CX. This is the longest chain with max being X. Is of size K plus 1, implying HY is K, at least K plus 1 contradiction. That's it. Very simple. Mirsky's theorem. Any question?
Is the max equal to Y, right?
No, max equal to X. Well, I'm talking about CX. CX is the longest chain ending at X. Now you go one more step together with Y. Maybe I should put a bracket here. So these together is a chain ending at Y. That's right. My arrow is here. Okay. Good. So let's now, do I have time to finish the proof of Dilworth's theorem? I think so. Yeah, let's try. We have 10 minutes. So now let's prove Dilworth theorem. There are several ways to prove, at least as I know, there are 3 ways. I will leave the other 2 ways as exercise. So one way is to use this conic theorem from graph theory. One way is to find the symmetric chain decomposition prove it directly. And one way, so these two ways I will leave it as exercise. One way is by induction. So let's see the disproof. Proof of Dilworth theorem by induction on the size of the poset, number of elements. The base case is very simple. The base case, when you have size 1, the singleton size of anti-chain is 1, and the chain decomposition is 1. Nothing to prove. So we need to look at the inductive step. Okay. For inductive step, let's think. I already tell you that we are going to use induction on P. So we somehow have to peel off one element from P. Right here is your P. You have to get rid of an element in P and look at a smaller poset with size P minus 1. Then we can use induction hypothesis. What would be the most natural element to peel off? The max or the mean, right? So we're gonna let A be the maximal element of P. Maximal means there's no other element such that A is less than the element. Okay. This just means there exists no B such that A is less than B. This is what it means. So what do we know? We know that by induction hypothesis, the first thing we're going to use induction hypothesis. If you look at this posets P prime, which is P with A removed, we can have some chain decomposition. The minimum chain decomposition of this guy equals to the size of the anti-chain. So there exists chain decomposition equal to C1 union CK for some K, and the largest anti-chain of P prime is also K. The width of P prime is K. This is induction hypothesis. You have the duality. Now, quick observation is if largest anti-chain of P with A in there gets larger, is K plus 1, then we are done. Because, so if width of P is K plus 1, then we are done, as this means what? Largest anti-chain of P is K plus 1. We just need to find the chain decomposition of size K plus 1. You just view A as a separate singleton chain. We have a chain decomposition of P of size K plus 1 as C1 dot 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 CK union singleton A is a chain decomposition of P. So may assume the widths remain the same. The largest anti-chain in P is still of size K. So let's now study this chain decomposition C1 to CK. Let's draw this picture. C1, Ci, Cj, Ck. This is my chain decomposition of P minus A, right? Chain decomposition P minus A. Since, well, we know the weights of P and P prime are the same. They are size K. So we have to somehow pick a nice size K anti-chain here and try to somehow merge, create a new chain decomposition with A incorporated to finish the proof. So this special anti-chain we're going to pick, this is the clever point. We're going to pick an anti-chain with, define this is the smart point. Define xi in Ci to be as the max element in Ci that lies in a max anti-chain. Remember, anti-chains of size K. Okay, so each, maybe let me use purple. Each chain we define x1, xi, xj, xk as the max in this chain, such that there is a chain of size, anti-chain of size k going through, involving this xi. This is well defined. First of all, we have to check this is well defined. It's indeed, this is well, xi are well defined as no size k anti-chain can miss a chain in C1 to CK. This is trivial. Every anti-chain of size K cannot take two elements from some chain. So if you completely miss a chain, you have size at most K minus 1. So this Xi is well defined. And this special anti-chain, maximum anti-chain we're going to look at is this X1 to Xk. So the next claim is that X1 to Xk form an anti-chain. The proof is simple. Suppose otherwise. Suppose say xi is less than xj. They are comparable. Yeah, this guy is less than this guy. Now we're going to consider an anti-chain of maximum size involving xj. Consider that A prime be a size k anti-chain containing xj. I know it exists by definition of xj. There is a size k anti-chain containing xj. It intersects at Ci chain as some elements xi prime, right? Here, xi prime. And define xi prime to be A prime intersect Ci. Then by definition, what's the definition? By choice of xi is the maximal element a size k anti-chain can possibly intersect Ci. That means xi prime must be less than xi, less than equal to xi in this chain, right? Choice of xi implies that xi prime is less than xi. Okay. But our assumption says xi is also less than xj. Implies that xi prime is less than xj, but they are in the one anti-chain. They are not comparable. Contradiction. Not comparable. Okay. One more minute, we'll finish the proof. Well, now we're gonna analyze, almost finished. So this is the C1, CK, CI. So we now know X1, we have these elements. Oops. Xi, Xj, Xk, X1. They are anti-chain of maximum size K. So if A is incomparable to any of x1 to xk, then we get weights of P is K plus 1. We've done those cases, right? If weights of P is K plus 1, you let A be a separate chain, we are done. So you may assume A is comparable. So A is comparable, but A is a maximal element. So that means A is bigger than xi for some I. Okay, the weight of P is K, so A must be comparable to one of them. Let's say this one. Let's draw it. A looks like this. A is bigger than xi. A is not in the chain. Remember, this is chain decomposition for P minus A. Okay, so A is outside. Now we consider this chain. You look at A and the bottom segments of this chain, Ci. So now let's C to be this chain, A union all the x in Ci, where x is less than xi, including xi itself. Now, one crucial thing we need to observe is that choice of xi implies what? Xi is the highest possible element we can choose in Ci, where a size k anti-chain can intersect Ci. That means if you remove this chain C, no elements above xi can appear in a size k anti-chain. In other words, if you remove this blue chain, the remaining has anti-chain size at most k minus 1. K minus 1. Now we are done because we use induction hypothesis on P minus C, we get the chain decomposition C1 prime to CK minus 1 prime, induction hypothesis, right? Then together with this chain C, we get a chain decomposition of size K for P. Done. Any question? I go over it a little bit, sorry. one quick question maybe, if you have any. No? Okay, then we will continue on Thursday, the class. See you guys.